Hello, everyone. So this is the classic Bernoulli equation question that you'll be asked. You have some container, and there's some hole in the bottom of the container, and it's just asking you to find out how fast is the water flowing out of the container. So this involves Bernoulli's equations, and it involves an assumption to make. So first, for Bernoulli's equation, what we know is we have to follow a streamline between 2 points. So what I'm going to do is I'm going to think of a piece of fluid that's up here that flows all the way down to this point too. And how does it get there? Well, I'm going to assume it follows some streamline like this. So the fluid goes down and shoop, it goes right out. So what does Bernoulli tell me? Bernoulli tells me that pressure plus some rho g h1 plus the fluid velocity at point 1 is equal to the pressure at point 2 plus some component due to the height of the fluid at point 2 plus the velocity at point 2. So we have to figure out a bunch of things about this problem. The first thing to realize is that the pressure that is exerted up here, atmospheric pressure, is actually the same as the pressure exerted down here. So if something is exposed to atmospheric pressure, like this fluid, this pressure is actually atmospheric pressure at this point. Right? The rest of this fluid is in free fall. There's no other way to cause pressure other than atmospheric pressure. So what we realize is that P1 is equal to P2 is equal to atmospheric pressure, and they totally cancel each other. What's the second thing to realize in these problems? Well, the second thing to realize is that at the top, we have some big area here, and at the bottom, we have some little area, A2 here. And if we look at the continuity equation, what does the continuity equation tell us? It tells us that A1 V1 is equal to A2 V2. Well, what does this mean? This means that if A1 is much, much bigger than A2, then V2 must be much, much bigger than V1, right? If this one's small, then this must be really big in comparison. And so what we do is we make an approximation. With V2 much greater than V1, we make the approximation that we can ignore this term compared to the term V2. So this is a critical assumption in doing these kind of problems. The other thing we'll do, and the last thing we'll do, is just set H2 equal to 0. We're just going to say that the height of this point is H2, and H1 is the height of the fluid above that point. So after all these simplifications, Bernoulli's equation just becomes rho g H1 is equal to 1/2 rho V2 squared. And a bunch of stuff cancels out still, like the rho's cancel out. And what does this leave us with? The velocity of 2 is equal to the square root of 2gh. You might recognize this. This is the formula for an object in free fall, right? Like, that's really amazing. Bernoulli's formula, this is a fluid flowing down with a bunch of other fluid around it, and the velocity of the fluid comes out just the same as if we had taken like a water balloon and just dropped it from that height. It's a really amazing thing, I think. If we plug in some numbers, the numbers I get are V2 is equal to 2 times 9.81 meters per second squared times 0.07 centimeters. Oh, got to be careful on a unit conversion there. And I believe you get 1.17 meters per second.